Welcome to AI Daily, your daily dose of artificial intelligence insights. I'm your host, David, and today we're diving into the fascinating world of deductive verification for continuous probabilistic programs. With me are Professor Alice, a renowned expert in formal verification, and Ben, a software engineer specializing in quantitative analysis tools. Welcome both.
Thanks for having me, David. It's a pleasure to be here.
Great to be here, David. Looking forward to discussing this topic.
So Alice, for our listeners who might not be familiar, what exactly are continuous probabilistic programs, and why are they so important?
Imagine a regular computer program, but with the added ability to make decisions based on probabilities and sample from continuous distributions. This is particularly useful for AI systems that interact with the real world, where uncertainty is inherent. Think about autonomous driving or medical diagnosis. Probabilistic programming allows us to model these scenarios more accurately.
Exactly, and because they are programs, we want to have guarantees they behave as expected. Formal verification helps us provide these guarantees.
That makes sense. Now this paper, titled Foundations for Deductive Verification of Continuous Probabilistic Programs, from To and Back, tackles a very specific challenge in this area. Ben, can you break down the main problem that the researchers are addressing?
The core issue is verifying the behavior of these programs when they involve continuous probability distributions and loops. Traditional verification methods struggle because they often involve calculating complex integrals, which can be computationally expensive or even impossible to solve exactly. This paper addresses this directly.
That's right. The crux of the matter is dealing with expectations, which are essential for defining the program's behavior. In the world of continuous distributions, these expectations are represented as integrals, and these integrals can be very difficult to handle directly.
So how does the paper propose to solve this problem?
Their key idea is to use sums to approximate these difficult integrals. Instead of trying to calculate the exact integral, they break it down into a series of simpler, discrete calculations. The beauty of this approach is that it allows them to leverage existing SMT, satisfiability modulo theories, solvers, which are typically used for verifying discrete systems.
In simpler terms, they're trading exactness for computability. By using sums, they can get close enough to the actual value while making the verification process feasible. And the paper proves that their approximations converge to the correct answer as the granularity of the sum increases.
Interesting. So this essentially allows them to use tools designed for discrete probabilistic programs to verify continuous ones. What are some of the real-world implications of this research, Alice?
The ability to formally verify continuous probabilistic programs opens up possibilities for building more reliable and trustworthy AI systems in safety-critical applications. Think about autonomous vehicles navigating complex environments or medical devices making critical decisions based on sensor data. This research provides a foundation for ensuring these systems behave as expected, even in the face of uncertainty.
It also means we can have greater confidence in the predictions and decisions made by these programs. This is particularly important in areas like financial modeling and risk assessment, where even small errors can have significant consequences.
That's a powerful point. It's reassuring to know that researchers are working on ways to ensure the reliability of these increasingly complex AI systems. Ben, did the paper reveal any challenges or limitations to the work, or perhaps opportunities for further research?
While the sum approach is promising, it introduces approximation errors. Future work could focus on developing more sophisticated approximation techniques that provide bounds on these errors. Also, exploring the application of this approach to a wider range of probabilistic programs and real-world case studies would be valuable.
Fantastic! This has been incredibly insightful. Thank you, Alice and Ben, for shedding light on this complex but crucial area of AI research. It's fascinating to see how theoretical concepts like sums can have such practical implications for building more reliable AI systems. Thank you, listeners, for tuning into AI Daily. We hope you enjoyed learning about deductive verification of continuous probabilistic programs. Please like and subscribe to receive more AI podcasts in your feed. See you next time.